Hello, hello, hello. This is section 2.3, the fundamental theorem of variation. Here's your journal choice. If you want to pause the video and write it down, feel free to do so. Okay, objective and what's the point? We are going to discuss and explore the fundamental theorem of variation today, and we're actually going to use it. This is kind of a shortcut to everything we did the last 2 days on sections 2.1 and 2.2, direct variation and inverse variation. Sometimes it's not necessary to find the actual k value, and that's what we're going to be concerned with today. We're just going to see the relationship between the variables in terms of like doubling or tripling and stuff like that. It should be a good section. I think you'll like it. Okay, this is the activity we will be doing in class tomorrow. So I'm going to skip through this. And here's what the actual theorem is going to be. Okay, and it's kind of generic, so stick with me here for 1 minute. Okay. If y equals k to the x to the n, that is, y varies directly as x to the n, and x is multiplied by c, then y is multiplied by c to the n, okay? What is this even saying? Okay, this will make more sense after the activity, but like I said, hang with me here and we'll see if we can make this sense. If y equals kxn, basically they're saying if you have direct variation, what do you guys already know about direct variation? Well, I know that the quantities grow or shrink together. So if one quantity gets bigger, the other quantity is going to get bigger. So what they're saying is if x is multiplied by c, let's say that c is 2. Let's say that I have some relationship and I want to double x, and I want to see what happens to y if I double x. Well, y is also going to be multiplied because x was multiplied, and if one is multiplied, the other has to be multiplied, and it would be multiplied by 2 to the n power. It's really going to depend on what happens to this exponent. Here is why. If I have y equals k x to the n, and like I said, let's say I want to know what happens when I double x. So now I have k times 2x to the n. Instead of x, I have 2x because it's doubled. This is no longer equal if I put a y there, because this is when it was equal. What did I do? I multiplied this side by something. I did not multiply it just by 2 though. I multiplied it by 2 to the n. So in order to keep these two equations equal, I have to multiply this by 2 to the n to keep them equal. That's all the theorem is saying. If you do one thing to the side with the x, then you're going to have to take it to the power on the other side. Okay? Now, this should be pretty obvious to you, knowing what we do about inverse variation. If you have y equals k over x to the n, that is y varies inversely as x to the n. And this time if we multiply x by some constant, then y is going to be divided. Why? Well, because if x is getting multiplied, x is getting bigger, what does y have to do? Y has to get smaller. How do you make it smaller? You divide. For the same reason as before, y equals k over x to the n. If I'm going to multiply x by 2, so now I have 2x to the n, this is doubled. What did I really do to the y? Well, I actually will have to divide it by 2 to the n because this is on the division side to keep it equal. Otherwise, they're not equal anymore. Okay? This is the big rule that is coming into play today. I used to call this pow-tributing when I teach exponents, taking everything inside that quantity to that power. Alright, this may be a little confusing right now, but the more examples we do, you're going to be like, oh, this makes so much more sense. So we're going to jump right into examples. I got these off of a worksheet. So if you need to pause to write these down, I encourage you to do so. I am going to work through all of these problems. I encourage you, after I do like problem 3, if you pause the video, you try to do 4, 5, and 6 on your own. And when I do 7, you try to do 8, 9, 10 on your own, and so on. You may be able to fly through these notes if this is easy for you. Okay? If y varies directly as x, and x is multiplied by c, then y has to be multiplied by what? C to the n. Because when it says vary directly, as we know we have y equals k x to the n. If I multiply x by c, so now I have y equals k cx to the n. To keep it even, I need to multiply this by c to the n so that they are equal still. Okay? If y varies inversely as x to the n, and x is multiplied by a non-zero constant, then c would have to be divided, because if one's getting big, the other has to get small. These are direct applications for what the theorem says. There's no real math here, just saying, did you understand what the theorem said? Okay, here's where we're jumping into the number problems. Suppose that in a given variation situation, the value of x is doubled. So how will that change if we have these cases? Okay, so we're always going to double x on all these. We will double x. Y varies directly as x to the third. So I'm going to write down the equation, y equals kx to the third. If I double x, what do I have to do to y? Well, that would give me y equals k times 2x to the third. So what did I actually do? I actually multiplied the right side of this equation by 2 to the third power, which is 8. So I have to multiply y by 2 to the third, or 8. Okay, how about this one? Y varies directly as x to the fourth. Y equals kx to the fourth. If I double x, now I have y equals k times 2x to the fourth. What did I actually do? I actually multiplied the right side of this equation by 2 to the fourth. So I need to multiply this side also by 2 to the fourth. Multiply y by 2 to the fourth. Okay, now this time I have y varies inversely as x squared. So I have y equals k over x squared. If I double x, y has to get smaller. Let's look at y. Y equals k over 2x squared. Because these are not the same. I actually have a 2 squared down below. So I divided the right-hand side by 2 squared. So this time I'm going y will be divided by 2 squared, or 4. Okay, y varies inversely as the square root of x. Let's not look at that one yet. I will go over it. Let's see. Y equals k. When it's the square root of x, that's actually x to the 1/2 power. We have not talked about that yet. I think this problem's a little premature. We're going to skip problem 6. Okay, this time we're going to triple the value of x. So this is going to change some things. Y varies directly as x. That means y equals kx. If I'm going to triple that x value, I now have y equals k times 3x. What do I have to do to y? Well, since it's direct, they both get big together. So I will multiply y by just 3, because there's no exponent in this case. Y varies inversely as x. Y equals k over x. If I triple x, y has to get smaller, so y is going to be divided by, y divided by what? Well, y equals k over 3x. No exponent again, so y will be divided by 3. Y varies directly as x squared. That's y equals kx squared. If I triple that x value, I now have y equals k times 3x squared. But I didn't multiply this side by 3. I really multiplied it by 3 squared, which is 9. So I'm going to y will be multiplied by 3 squared, or 9. I kind of like to use the exponents here instead of simplifying all the way, because you can see The base number is what you're doing to the variables. Are you doubling them? Are you tripling them? And the exponent is what that inverse relationship was about, the squaring. Okay? Y varies inversely as x to the third. Y equals k over x to the third. If I triple x, y equals k over x to the third. This is inverse, so if this one gets bigger, y needs to get smaller, so y would be divided by 3 to the third in this case. I hope this is making sense to you. Like I say, usually the more practice we do, the better we get, so we're going to look at more practice still. Here we go. Suppose that a varies directly as the fourth power of b. So I'm going to write that down. A equals kb to the fourth. How does the value of a change if b is doubled? Okay, if b is doubled, where's my pen? Hello. It's not wanting to move for me. I have a equals k times 2b to the fourth. This is direct. So they're going to get big together and they're going to get small together. If I'm doubling b, I'm really multiplying a by, do you see it? 2 to the fourth. What if I quadruple b? Well, that means a equals k, not double, so not 2b. This time I'm going to have 4b to the fourth. A is also going to get bigger still, so I will multiply a by 4 to the fourth. What if I multiply b by 5? A equals k times 5b to the fourth. A still has to get bigger because b is getting bigger, so I multiply a, I don't know why I didn't write by there, by what? 5 to the fourth. If b is multiplied by 6, I'm sure you can figure out the pattern now. Multiply a by 6 to the fourth. Alright, this is trickier. If b is multiplied by 1/4, I will have a equals k times 1/4 b to the fourth. What's going to happen to a? Well, you could use this shortcut that we've been doing. You could say multiply a by 1/4 to the fourth. You can say that. But I want you to think for a second about what this means. If b is multiplied by 1/4, it's really the same thing as dividing it by 4. You could have also said divide by 4 to the fourth, and it would have been the same thing. In fact, I think it makes more sense. Which leads us right into this example. B is divided by 3. If I have a equals k times, that would be like b divided by 3 to the fourth. If b is getting smaller, this is direct variation. A has to get smaller. So I'm going to divide, just like I was dividing here, because I had to match up with direct. Divide a by what? 3 to the fourth. Okay, so in a nutshell, direct variation. They will either both be multiply or divide because they get big together and they get small together. The base number is what you're actually doing to the value. So if you're doubling, it's 2. If you're tripling, it's 3. And then that exponent comes into play for whatever the direct variation relationship was. All right, let's try these. 17 through 20. Suppose that p varies inversely as the fifth power of n. So we're going to go ahead and write this down. P equals k n to the fifth. Oops, that's not right. It says inversely p equals k over n to the fifth. Okay, make sure you're reading these problems carefully. How does the value of p change if? Now remember, on these, since it's inverse, if one quantity is getting big, the other will get small. The opposites of multiplication is division. That's how we do this get big, get small thing. So if n is doubled, p isn't going to double. It's going to be divided by something. What's it going to be divided by? Well, I could write it down. P equals k over 2n to the fifth will be divided by 2 to the fifth. If n is quadrupled, p has to get smaller. So p divided by 4 to the fifth. If n is multiplied by 6, p has to be divided by 6 to the fifth power. If n is multiplied by 1/2, there's two ways we could do this. P could be divided by 1/2 to the fifth, you could say that. Or if you think of this as n is divided by 2, then you could say p was multiplied by 2 to the fifth. I think this way is nicer, but it's up to you. I think we're almost done. Oh, this is the last slide. Let's look. Yeah, it is. Okay. Use the fact that volume of a cube varies directly as the cube of its length, width, or height. So let's write volume equals k. This is direct. So let's say L to the third. Okay. A small cube-shaped planter has a length that is 1/5 as long as the length of a large one. How does the amount of dirt each planter can hold compare? Well, if it's 1/5, direct goes together, it'll be divided by 1/5 to the what power? Third. Or if you thought of this as multiply by, this is completely wrong. A small cube-shaped planter. I'm going to draw a picture. You're going to like that. Oh, that's good. Has length that is 1/5 as long as the length of a large one. So there's a small one. There's a large one. Oh my gosh, pretend that's good. How does the amount of dirt in each planter can hold compare? Well, we should say it like this. The small one has 1/5 to the third as much as the large one. You could say it like that. Or you could say divide large one by 5 to the third. I think either way is fine. Or you could say multiply by 1/5 to the third. This was not right, what I wrote before. When asked to compare, you should probably give some more words than what I was writing. Okay, a large cube-shaped tank has a width that is 2.5 times as great as the width of a smaller one. How does the amount of water? Again, here's the big one. Here's a small one. This is 2.5 times as great. How does the amount of water each tank can hold compare? So the bigger is going to be 2.5 to the third times greater in volume. The dimensions of a cube-shaped recycling bin are doubled. How do the volumes? Same thing. 2 to the third. I think you get the idea. Okay, tell what effect multiplying x values by 1/3 would have on y values. This is direct. So if I multiply the x by 1/3, what am I going to do to the y value? Multiply by 1/3. If I multiply x by 1/3 here, I'm actually going to multiply y by 1/3 squared because of the exponent. In this example, this is inverse, so if I multiply x by 1/3, I'm going to divide y by 1/3. I think that's weird when we say divide by a fraction. I probably would say multiply by 3. It's up to you. And in this one, if w equals k z to the n, and z is multiplied by a constant c, what happens to w? Multiplied, because it's direct, by c to the n. If w equals k over z to the n, so if you have inverse, z is multiplied by c, what happens to w? It would be divided by c to the n. That's just the same as those first two questions, really, on those examples today. Lots of examples today. The more practice, the better. Really, you just need to keep straight that on inverse, if one is doubled, you're going to divide the other. They're going to be opposites. Multiply and divide. Okay? And really pay attention to the exponent. All right, make sure you have, if you have any questions that you ask, we really need to do lots of practice on these. And don't forget you have a quiz this week, so study up.